Okay, the next thing we're going to do here is revisit one of your favorite theorems, but we're going to look at it in a different context. Your favorite theorem, of course, the correct answer being the mean value theorem. Okay, we're going to look at the mean value theorem again, but this time we're going to look at it from an integral perspective. And before we do that, I guess it's probably worth reviewing the MVT for derivatives. So if it ever just says, or I say the MVT and I don't say for derivatives or integrals, you have to assume we mean for derivatives. It's the first one we learned. And if you want to be discussing the MVT for integrals, you're going to have to say the MVT for integrals. Okay? Otherwise, we'll assume it's the MVT, which is for derivatives. So remember, what was the if part of the MVT? Continuous on closed, differentiable on an open. So let's just draw an example that looks like that, something like that. Here's A and here's B. Continuous on the closed and then differentiable on the open, so no cusp for vertical tangent. Then there has to be an x value strictly on the open interval from A to B, where the slope of the secant line, which you could draw like that, is equal to the slope of the tangent line. So in this case, I drew two of them, C sub 1 and C sub 2, where the average rate of change equals the instantaneous rate of change. But it has to be on the open interval. So if one of the values ended up being the endpoint, that's not the one we're looking for. And of course, we can remember that pretty easily because M means mean, right? Which means average. And so the slope of the secant line, if you recall, is your average rate of change. So that's where that ties in. And of course, back in Algebra 1, mx plus b, let me try that again. Mx plus b, m represented the what? The slope of the line. And so that you can remember that as your tangent line slope. So the MVT is the same as the slope VT, whereas the IVT is the YVT for proving Y values. Good. Well, now we have the MVT for integrals, and here's what it says. It says if f is continuous on a closed interval. That's it. Doesn't need to be differentiable in the open. If we have a function that's continuous on a closed. Now remember that if a function is continuous, we know it is also what? Integrable. Integrable. So here's what the MVT says. If you have a function that's continuous on the closed, then there's an x value, c, in the what? Closed interval. That's dramatically different from the MVT for derivatives. This says that the value of x we're looking for could be exclusively an endpoint. Such that this is true. Such that this is true. So just soak it all up. Take it all in. Oh, whoa. What a profound then part. What an awesome conclusion. Well, what does that mean? Well, it means that the net accumulation on the interval from A to B, which could represent the area, right, if f of x is non-negative, is equal to B minus A, which is the width of your interval from A to B, times f of c, which is just some y value at that x value. When we did Riemann sums, we know that that could represent the height of what shape? When you multiply h times w, you get the area of what shape? A rectangle. So this is going to be some rectangular area. And we're basically saying, if you want to think about it in terms of area, then the area under the curve, if you want to think of f of x as being entirely non-negative, then the area under the curve with the variable top is going to equal to the area of a particular rectangle on the same interval from A to B, whose width, of course, is B minus A, and whose height is the function value at the C value the theorem guarantees. All right, so here's what it looks like geometrically. Let's say I have a function f of x. I'll trace over it in red. It's continuous on the closed interval from A to B. Because it's entirely non-negative, the integral represents the area. And it's pretty easy to conceptualize this when you're thinking of non-negative regions. So if I took the integral from A to B, it would be that shaded region right there, and it would represent the area. Yeah? So what the theorem tells us then is there is going to be an x value, call it x equals c, such that if I go up to the function there, to f of c, and I use that as the height of a rectangle all the way across on the same interval, then the area of the rectangle, which I'll highlight in green, is going to be exactly the same as the area under the curve in red. Okay? So in this case, this little red region above the rectangle, and this little cutout region above the curve but inside the rectangle, those would have to be numerically equivalent, right? Okay. So the mean value theorem is saying that that y value exists. And there's an x value that could be at the endpoints or on the interior that generates the y value, at least one. Now, it's pretty easy to see why that works, because if you look at this little meter stick, which is a horizontal line, if you use the height of the rectangle down here at the absolute minimum of the function f of x, you can see you get a rectangle whose area is definitively too small, right? It doesn't give you the area under the curve. If you also then went up here and used the absolute maximum's y value for the height of the rectangle, you see that that's going to be an egregious over-approximation, right? Now, because the function is continuous, and we go from something that is definitively too small to definitively too big, as I basically slide this ruler up, there has to be, through a continuum, some place where the height is just right. The one that Goldilocks preferred because it was baby bears. There's a just right height. And that just right height is f of c. And the theorem says there's an x value on the closed interval that generates it. Okay? Now, the f of c is actually almost more interesting than the c value itself, but they're both pretty awesome. F of c ends up being what we call the average value. And when we say value, we mean y value. Okay? It's the average height of the function, if you want to think about it like that. Now, that's pretty significant because if I had your grades, let's say over time in weeks, whatever, or days, I'm plotting your grades. Okay, and you had like a grade here and then a grade there, and your grades are getting good. Now you have hundreds, and then you did poorly, and then you did better. You recovered, whatever. Can I connect the dots on those? Is this a continuous function? Do your grades happen through a continuum? If you made an 80 on one assignment and a 90 on another, does that mean that you have an assignment where you made every possible point score between 80 and 100 or 90, whatever I said? No. No. So if I wanted to find your average grade, assuming they were all weighted the same, I would just add up all your grades. Let's say you had 10 of them. Get the aggregate sum and divide by 10, right? No problem finding the average. But for things that change through a continuum, like what? Speeds, as you accelerate, your speeds change through a continuum. Temperatures rise and fall through a continuum. What happens through a continuum? Tides rise and fall through a continuum. Anything that changes through a continuum, if you wanted to figure out what the average value was, you couldn't do it by the discrete method, right? So that's where this is important, because let's think of this function maybe in red as temperature, right? If you wanted to figure out what the average outdoor temperature was, you might conduct an experiment, all right? You might go outside every hour and take a reading and write it down. And at the end of the day, maybe you have 24 points. You could add up all 24, divide by 24, and you'll get your average approximate temperature, right? If you wanted a better approximation, what could you do? Instead of taking a reading every hour, you could take a reading every 30 minutes, right? That's more work for you, but at least it's fun, right? Or you could take a reading every 10 minutes, or every minute, or every 20 seconds, or every second. Wow. Have someone hand you energy bars while you're doing that, because you're going to need the fuel. That's a lot of work every second, right? Or every nanosecond. Woo! Okay? The more points you have, the better results you're going to get, right? Because they change through a continuum. All right? So what this is if you have infinitely many y values, there's no way to physically add up all of these y values, right? Because there's infinitely many of them. And even if you thought you finished after you added up infinitely many of them, you would then need to divide by however many there were, which would be infinity. That's going to be very difficult, right? But yet you still might be interested in finding the average value. There is a way to do it, okay? That height right there of that rectangle is the average value. And you can find the average by what's going to be what I'm going to call the density method. Now, here's what really might happen in the real world. You might go out there and take readings for temperatures, right? Every 30 minutes, however often you want it to. Now, your TI calculators, believe it or not, have the ability to fit a curve to the data. Whether you predict it's going to be like a sinusoidal curve or an exponential curve, your TI calculators can fit a curve to the data. Okay? Once you have the curve, you can actually find the average value using the curve, which will take into account all of the data points in between the ones that you miss when you collect it every so often. It uses the inferred values in between there, so it's a little bit more accurate. So let's see how we can find the average value. If f of c represents the average value, and this is what the theorem gives us, all we have to do to solve for the average value, f of c, is divide through by b minus a. So you end up with this. You get the integral from a to b of f of x dx, which gives you essentially the area or the net accumulation, and you divide it by the width, b minus a. So the average value ends up being the integral over the width. The average value is the integral over the width. How do you find the average value? Integral over width. Right. What does integral over width give you? The average value. And what's nice about it is it's the average y value. So if you have anything measured on the y-axis, temperature, speed, whatever, water consumption, I don't know. Can you do that through a continuum? Who knows? I'm not going to doubt you. You can find the average whatever value, okay? And how do you find it? One more time? Integral over the width. And it's pretty easy to look at from the area perspective, because if you think of the integral as being area, that's basically a height times a width. And if you divide through by the width, you get the average height. So it's the average height of the graph as well. And it's a little more accurate. I say it's the density method because you're taking the area and dividing out one of the dimensions, getting back to a singular dimension. Okay, so pretty cool. Now, you might see the integral over the width written a little bit differently. You might see the b minus a, which is in the denominator. You might see it pulled out front. So if you ever see like an integral with 1 over a number stuck out front, especially if that number is the difference of your intervals of integration, chances are it's an average value. And you're going to be asked to interpret that. So let's jump to an example. Example 12, calculator. Okay? This is pretty relevant right now. The temperature outside has changed pretty dramatically. Boy, that's a whole different kind of change, dramatically. It's a little chillier than it was this morning. It's kind of damp. Yeah, okay, there you go. Hey, the apartments are still there. So is the tree. Okay. In New Braunfels, anyone ever been there? The temperature in degrees Fahrenheit, T hours after 9 a.m. was modeled by this function. So maybe some person went out and collected data, got their TI calculator out, plotted it, fit a curve to it, and they gave us this. Pretty appropriate though, right? It's a sinusoidal curve. The temperatures go up, and then they go down, then they go up, and then they go down. I like it. It says to find the average temperature during the 12-hour period from 9 a.m. to 9 p.m. Okay, now it says to find the what? Average temperature. Is that the average value? Yeah, or is it the average rate of change? Whoa. We got to be careful. We have two averages now, right? Average rate of change and average value. Average rate of change is change in y values over the width, right? Difference quotient. Average value now is the what over the width? Integral. So they're both going to involve some kind of subtraction, right? The definite integral, when you evaluate it, is subtraction over the width, and then the average rate of change is change in y values over the width. If you're not sure, go ahead and just think about what it is the function gives you. We have temperature, big T in degrees Fahrenheit, with respect to time in hours. And if we're trying to find the average temperature, what are we measuring on the y-axis? Temperature. So if you ever want to know the average y value, that's the integral over the width. So let's go ahead and set it up. You want to get in the habit of labeling your integral. So we'll say the average temperature is equal to the integral over the width. Well, that's going to be the integral from. Do we go from 9 to 9 if we're going from 9 a.m. to 9 p.m.? It says let T represent the hours after 9 a.m. So 10 a.m. would be how many hours after 9? 1. So we don't go from 9 to 9, rather we go from 0 to 12. And here's a nice little tip. If it's a calculator question like this one, and you have your function named like big T of T, all you need to do is put big T of T dt there. You don't have to waste the time putting the 50 plus 14 sine of pi T12. So it wouldn't be wrong to do that, but it's a little bit faster. So there's the integral divided by the width, right? Which would be 12 minus 0. And just like in your difference quotient for your setup point, you need to show the difference in the denominator. So it's almost like the difference quotient, which would give you the average rate of change. Now, before we go to the calculator, let's see what the units are going to be, because it's kind of interesting. If I were to look at the units on the top, units of big T, that's degrees Fahrenheit, times units of dt, that's hours, right? So my units in the top are Fahrenheit hours. Have you ever heard of units like that, Fahrenheit hours? Kilowatt hours, have you heard of kilowatt hours? Yeah, it's called an aggregate unit. It's a unit of consumption. So this would be like Fahrenheit hours, the total number of degrees we accumulated. And then in the bottom, you divide it by 12 minus 0, which is in hours. What happens with the hours? Divide out and you get your average degree temperature. So the units work out beautifully. Remember, stoichiometry is always a good thing to consider if you're not sure whether to use the derivative or the integral. Because if you need to divide to get your desired units, you probably want to do the derivative. If you need to multiply to get your desired units, you're probably going to take the integral. Okay, so from here, we'll just go to the calculator. Calculator, dude. And we'll pull up the calculator here, pull up our work here. So if it's just a single calculation, like a little multiple choice question, feel free to go ahead and type this directly into your home screen. But chances are we're doing like a free response question, and we have to use that equation multiple times. So what I would recommend is to type it into Y1 and make sure you get it in there one time perfectly, okay? 50 plus 14 sine of pi x divided by 12. What mode should we be in? Always in here? Radian, okay? Let me get rid of that. Okay, so now that you have it in Y1, you go to the home screen. We don't really care about the graph at this point. We got it set up, and if you have the new math print, you could go alpha y equals. Let me try that again. You can actually use the horizontal division bar, which is nice because it makes it look exactly like we're going to do. So now that you're in the numerator, now you can math 9 it, right? And we're going to go from a 0 to 12. And we need to recall what we typed into Y1. So you can get there quickly by alpha trace. And there's your shortcuts to your y's. And then, of course, with respect to x. Now, on the bottom, of course, 12 minus 0 is 12. So you could just put 12. But in general, you might have some pretty ugly numbers there. So you can type it in if you're not sure. Or if you're doing the slanted division bar, make sure you put them in parentheses. Parentheses 12 minus 0. And there you go. There's the integral over the width. One setup, one type it in, hit enter, you're done. And now you just write that down on your iPad/paper pad. 58 point, how many decimals do we report? 3. So either 912 or 913, and then units of degrees Fahrenheit. So the interpretation would be then from 9 a.m. to 9 p.m., or on the 12-hour interval from T equals 0 to 12 hours, the average temperature in New Braunfels was 58.912 degrees Fahrenheit. Okay, we found it. Now, notice that 12 minus 0 is in fact 12. You could write it like this if you wanted to. I just like to go integral over width, but College Board might give you something like this in the stem of a question. And they'll give you the temperature function to be whatever we said in degrees Fahrenheit. And they'll give you something like this, and they'll say not only to evaluate it like we did, but they'll say to interpret it. And if you see something like that, you're like, what the heck is a 1 over 12 doing in front? Guess what? Whenever you see 1 over a number in front, especially when it's this number minus this number in the denominator, this represents the what? This represents the average value of this function. It's the average value of this function on that interval. So you would look at that and be like, oh, 1 over 12. Okay, what is this measuring? What did you say, temperature? Okay, this is the average temperature then in degrees Fahrenheit on the interval from T equals 0 hours to T equals 12 hours. Okay, cool, got it. They've been doing that a lot more lately, 1 over a number. So if you ever see a number outside the integral, that's probably what it is. All right, kind of interesting, right? Is that a reasonable answer? Yeah, very reasonable. Let's see what the graph looks like, just for kicks and giggles. It's a sinusoid. The plus 50 moves it up, right, which is now your sinusoidal axis. The 14 is the what-litude? Amplitude. So we're going to go up to a high point of what? 50 plus 14, which would be 64, and a low point of 36. So I'm going to graph it from 0 to 12. That's a 12-hour interval that we're looking at. And I went from 0 to 70. If you hit graph, here it comes. I didn't turn it on. Sorry. Anticlimactic. All right. There we go. Graph, baby, graph. Ooh, it's getting warm in here. Oh, it's starting to cool off again. There you go. Now you can see that the average value might be somewhere in here. Okay, do we know what the average value is? We just found it. Let's go ahead and graph it. Now here's what you could do. Since we calculated it on the home screen and it's still right there in its full decimal glory, let's hit stow alpha A. All right? So now it's in there as A. You don't generally want to store things as X because the calculator always overwrites stuff to X. So now if we go to Y equals, we can graph A right there, alpha A, which is a horizontal line, and you should see it cut kind of right through the middle there. That's the average value. Sweet. Now, you'll notice that we very rarely will refer to, in earnest, the mean value theorem for integrals, because what we're really after from the mean value theorem for integrals is the average value. It's kind of the more important idea there. But you might be asked to find the value of C guaranteed by the mean value theorem for integrals. So how would you do that? Well, you would find the average value like we have right here, and you would set the average value equal to the function itself and solve. And graphically, that's going to be where these two do what? Intersect. So let's go ahead and find where that happens. Okay, so second trace now, number 5, enter, enter, enter. Come on in. It'll find one of them first. I don't care which one. There it is, 2.636. So that's one of the values guaranteed by the theorem. So what does that mean? Yeah, approximately 2.636 hours after 9 a.m. The outdoor temperature was 59 point blah blah, 58 point blah 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 blah. So notice, just like the mean value theorem for derivatives, this is saying that there had to be at least one point during that interval where the average temperature during that time interval actually occurred, right? We're just talking about temperature instead of rates of change. Yeah, that makes sense. And we know there's another one over there as it cools back down through the continuum. So this one has 2 values guaranteed by the theorem. Pretty neat. Now let's do one last thing before we go to the next one. And this is just for fun. This one's just for fun. Remember, geometrically what we're saying is that the area under the blue curve on this interval from 0 to 12 is equivalent to the area of the rectangular rectangle under the red curve. And I use curve in quotations because it's straight. Remember your calculator. I would never recommend doing this on a test or anything, but it is kind of fun, especially the color version. Let's go from the graphing screen, second trace, number 7, and it's going to put us on the blue curve first, okay? Let's integrate it from 0 to 12, and it should give us the aggregate units in Fahrenheit hours, and it'll shade it. Ooh, look at that. It's covering up the red line. Pretty. Pretty, right? Being unicorns, we like seeing that much blue. Oh, boom, there it is. 706.952. Now, do you think anyone in the world has ever found the average value just by calculating the integral and forgot to divide it by the width? You think anyone has ever done that? Yeah. If you compute just the integral from 0 to 12, you're saying, oh, the outdoor average temperature was 706.952 degrees Fahrenheit. Whew, it was a hot day. Hot day. I remember that day. I was dehydrated. Yeah. Whew. That's not a reasonable answer, huh? A raspa. Yeah. 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 If you can find the building, I think the building melted, not just the ice. Now, watch this. Second trace, number 7. If we toggle up to the horizontal line and we do the same thing from 0 to 12, watch this. It'll trace out over the blue, and I should get the same answer, right? 706 point whatever, that really hot day. Boom, 706.952. So we've just confirmed geometrically that the area, we don't like seeing that much red if we're unicorns, though, right? Right. It's the exact same area, right? The point is, it was a very hot day, unreasonably hot, doesn't make sense. Divide it through by the width, and you get back down to 59. Yeah. All right, very cool. Here's what I'm going to have you do. Go to example 13 now. Go to example 13, and I want you to do it on your own because you can do this one without a calculator. The math works out pretty decent. Find the value of c guaranteed by the mean value theorem for integrals for the function f of x equals 1 plus x squared on the closed interval. While you're doing that, I'm going to draw the picture. If you haven't done so already, I'm going to try and catch up with you. And while y'all are finding the value, I'll draw it, and then we can kind of match answers, and it should make sense geometrically. On your mark, get set, go. Remember, the mean value theorem is for integrals is okay with looking for values that fall at an endpoint. There we go. Had a little trouble drawing it to scale. Okay, that looks better. All right, so very quickly, for the bell catches us, we're going to take the integral from -1 to 2, and we're going to divide it by the width 2 minus -1. And that's going to be the average value, so you find it first. So if you integrate, you get x plus 1/3 x cubed, evaluated from -1 to 2. Now, instead of dividing by 3 at this point, you could bring the 1/3 in front. And when you evaluate it, kind of leave the 1/3 out there. You're going to get 2 plus 8/3, and then you're going to get minus a -1 minus 1/3. And if you simplify all that, you get 2. You get 2. You get 6/3, which is 2. So that means the average value is 2. Now, to figure out the values where that occurs, you now set that equal to your function. And you get x squared equals 1, so x equals plus or minus 1. Now, notice both -1 and +1 fall on the closed interval, which means both of them fall into the theorem, okay, because we can have an endpoint. So graphically, what it looks like is you have this, bless you, this rectangle, and the area of the rectangle at the left endpoint, where it'll intersect again, is equivalent to the area under the curve in blue. So it still doesn't look like it, but this little region in red and this little region in blue are supposed to be equivalent. Of course, I didn't draw it to scale. But that's a fundamental difference. The MVT for integrals, you can include the endpoint. Nothing outside the interval, but the endpoint's okay. All right, we'll finish the notes tomorrow. We'll have a little quiz tomorrow, too. Little quiz over MVT for integrals and integration. Have a good day.